Good morning, everyone. My name is Haizu, a PhD student from Delft University of Technology. We feel very sorry not to be at the MRS. This is due to medical and visa issues. Now I'm going to present our work on probabilistic multi-robot collision avoidance using buffered uncertainty-aware Voronoi cells. Multi-robot collision avoidance is a fundamental problem when deploying a team of autonomous mobile robots. For example, a team of drones performing coverage tasks. In real world, robot positions are generally obtained from some sensors and an estimator, and are not perfectly known, so the motivation and goal of this work is to take account of robot localization uncertainty into the multi-robot collision avoidance problem. Many methods have been studied for multi-robot collision avoidance in deterministic scenarios, such as velocity obstacle-based methods and model predictive control. Those methods can be extended to the probabilistic scenarios by considering bounded localization uncertainty, or formulating a chance-constrained MPC. However, they could either be too conservative, like the robust MPC, or require too much communication, like the chance-constrained MPC. Our work is built on a recent method, B-UAVC, the buffered Voronoi cells. We extend it to probabilistic scenarios and present buffered uncertainty-aware Voronoi cells. The main contribution of this work is a method to compute uncertainty-aware Voronoi cells among robots with chance-constraint buffer, and to use them to achieve probabilistic collision-free. Adding a chance-constraint buffer is to ensure that the collision probability among robots is below a specified threshold. We also evaluate the method in real experiments with quadrotors. To formulate the problem, we consider a team of robots in which each robot at position P sub I with radius R sub I. We assume that the robot position P sub I is according to a Gaussian distribution. Each robot knows other robots' position information by communication or sensing. Given a goal position G sub I for each robot, the objective is to compute a local motion for each robot to make progress towards its goal, while being probabilistic collision-free with any other robot. That is, the collision probability between each pair of robots should be smaller than a specified threshold, delta. To begin with, let's give a brief overview on the buffered Voronoi cell method we built on, where robot positions are perfectly known. First, a Voronoi diagram is constructed by computing a separating hyperplane between each pair of robots based on their current positions. See the figure, for example, with two robots. Then, a buffered Voronoi cell is computed for each robot by shifting the separating hyperplane towards to the robot with its physical radius r. And such a cell can be computed for each robot in the system. Finally, collision avoidance among robots is achieved by restraining each robot motion to be within its own buffered Voronoi cell. Now let's consider the robot positions are not perfectly known. The first question would be how to construct an uncertainty-aware Voronoi cell. Similar to the B-UAVC method, we assume that there is a hyperplane represented by a linear equation A sub ij p equals B sub ij, which separates the two robots at position P sub I and P sub j. Note that the two positions are not deterministic and are according to Gaussian distributions. So, a very intuitive idea is that the robot with larger localization uncertainty should get a larger share of the workspace. So, we rely on the concept of best linear separator for two Gaussian distributions where a clustering problem is formulated. Consider that the hyperplane classifies the workspace into two clusters, one on the robot I side described by Aij smaller than Bij, and the other on the robot J side described by Aij larger than Bij. For point clustered to each side, it should be more likely according to the same Gaussian distribution. Then we can obtain the misclassification probability Pi of a point from the I side while clustering to be close to J. Similarly, such a misclassification probability Pj can also be obtained. Next, we can compute parameters of the separating hyperplane Aij and Bij by minimizing the misclassification probability. We rely on an efficient algorithm presented in the reference shown here to solve for Aij and Bij. Finally, by computing such a hyperplane for each pair of robots, an uncertainty-aware Voronoi cell for each robot is constructed. After getting the uncertainty-aware Voronoi cell, similar to the deterministic B-UAVC, we first add a buffer, beta r, considering the robot physical radius. However, this is not enough since the robot positions are uncertain, and there is still a probability of collision between them. So, in order to make the collision probability smaller than a specified threshold delta, we add another chance constraint buffer, beta delta, to the cell, and finally get the buffered uncertainty-aware Voronoi cell for each robot. For simplicity, we call it B-UAVC. In our paper, we show that the value of the buffer beta delta is given by this second equation. And we show that any two robots are probabilistic collision-free if they remain within their B-UAVC. For proof, you can refer to our paper. We then use those computed cells for multi-robot collision avoidance. For robots with single integrator dynamics, the optimal control input of each robot can be computed by making the robot always move towards a local goal G star, which is the closest point inside the cell to the goal position G. Note that the cell computed for each robot is represented by a set of linear inequalities, so finding such a closest point G star can be solved efficiently using quadratic programming. For robots with high-order dynamics, we use a model predictive controller. In each time step, each robot solves an optimization problem to minimize the distance to the goal, by restraining the planned mean trajectory to be within the buffered uncertainty-aware Voronoi cell, and assuming that the position uncertainty remains constant in the short planning horizon, probabilistic collision avoidance is achieved. To increase safety level for high-order dynamic robots, we also add another extra safe deceleration buffer for each robot, which is defined by the minimum required distance for deceleration to zero velocity, so robots always have enough room for emergency stopping. We did simulations with single integrator robots. Position measurement noise is added to each robot in simulations. As shown in the video, the deterministic B-UAVC method always leads to collision because it doesn't account for localization uncertainty and drives robots close to each other. Instead, by taking into account the uncertainty and add an extra chance constraint buffer, our method successfully navigates all robots without collisions. We also compared our method with chance constraint MPC by simulating a team of quadrotors. The results show that the minimum clearance among robots using our method is larger than that of the chance constraint MPC, which indicates that our method is more conservative. Nevertheless, chance constraint MPC requires robots to communicate their future planned trajectory and associated uncertainties, while instead, in our method, communication among robots is not necessarily required. In real experiments with drones, artificial Gaussian noise of variance 0.04 meter is added to the motion capture system measurement data. We observe that the two drones can safely avoid each other. In the first scenario, the two drones are required to swap their positions. In the second scenario, one drone is hovering, while the other is required to bypass it. In the third scenario, the two drones are following two crossing paths while avoiding each other. One drone is tracking a path of a shape number 8, and the other is swapping positions between 2 points. In conclusion, in this work, we present a probabilistic multi-robot collision avoidance method. Probabilistic collision-free is achieved by restraining the robot motion to be within its buffered uncertainty-aware Voronoi cell. Construction of the cell relies on the best linear separator between two Gaussian distributions and the computation of a chance-constraint buffer. Thank you for your attendance.